Hey, geometry, welcome to 3.5 proving. We're going to get into some serious proof at this point. I kind of said it was coming. This really is where we're going to really kind of start to dive in. This doesn't all have to be super easy at first. This can be a bit of a challenge getting used to the proof process that we're going to go through. And I'm going to throw up a Google document here as well of, and we're going to kind of keep adding to it of different justifications, postulates, theorems, definitions, things that we have that we'll use in proof, because that is a big part of it, is kind of basically walking through your steps and justifying your steps to show, like, I know this because of this. I know this is true because of that. I know this is true because of that. And because all this is true, I've now proven that if, based on this information, we can conclude this result. So that's the overall idea. We're going to focus on parallel at first, but we're going to be doing various proofs throughout the year. And I kind of alluded to this stuff coming. I didn't want you to worry too much about it at first, but let's go ahead and dive in. So first, we're actually going to introduce the concept of a converse. A converse is if we have a theorem or something we know is true, then the converse may be true. The converse is kind of like if we have some statement that if A, then B. If A is true, then B is true. Well, the converse of that would be if B is true, then A is true. And sometimes that's the case. Sometimes the converse is true. Sometimes the converse is not. So like if I can prove, this will be a concept we'll deal with later, but like the idea that a square is like, so if it's a square, then I know that it is also meets the conditions to be a rectangle. So because of the way that we define the square as a subset there. But the alternative is not true. If it's a rectangle, that doesn't necessarily mean it's a square. So that's the in that case, the converse is not true. But in these four here, the converse is true, and these are our different like corresponding angle postulate and alternate interior angles and so on. So these are the converses. Before those ones said the converse are not the converse, but the corresponding angles postulate said if you have parallel lines cut by a transversal, then corresponding angles are congruent. Well, this reverses that. If two lines in a plane are cut by a transversal, notice they don't say parallel lines. If two lines are cut by a transversal so that a pair of corresponding angles are congruent, if we know that the corresponding angles are congruent, then we know that then the lines are parallel. The two lines are parallel. So this actually justifies, and this is where we're going to be proving parallel. We can use these converses to prove that they're parallel. If we can establish some corresponding angles that are congruent, then we know that the lines that we're dealing with are parallel. And that kind of goes through all these. I'm going to speed up going through the rest of these. So the converse of the alternate interior angle, basically, if two lines in a plane are cut by a transversal so that a pair of alternate, I'm just going to abbreviate interior angles are, and I'm just going to write congruent. If you have alternate interior angles aren't, then I'm just going to say the lines are, and I'm just going to write the symbol, are parallel. If we have alternate exterior lines, so if we have a setup where we have a couple of alternate exterior angles are congruent sign. If our alternate exterior angles are congruent, then that tells us that those lines must be parallel. So then the lines are parallel. And finally, if we have consecutive interior angles, this is a little bit slightly different. Remember, consecutive interior, they're supposed to add up to 180 if the lines are parallel. So that's what's going on here. So if we're cut by a transversal so that a pair of consecutive interior angles are supplementary. Then the lines are parallel. So that's a little different than all the congruent ones. Then I'll just say this: the lines are parallel. A bunch of different ways of proving that lines are parallel. So in this example here, we're identifying parallel lines based on some given angles. Notice they don't tell us that these lines are parallel. This is an L, by the way. It's supposed to be kind of like a cursive L. And this is A, B, L, M. So they're telling us that these angles are congruent. Angle 1 is congruent to angle 2. All right, so what if that's true, which two lines have to be parallel? Well, these would be corresponding angles with this transversal crossing these lines. And so that would tell us that lines A and B, A and B are parallel. So I'm going to just say, line A and line B are parallel. And that would be the converse of the corresponding angles postulate. Converse, that'd be this number 1 up here. Converse of, I'm just going to write kind of shorthand, corresponding angles postulate. That would be how we could justify lines A and B, because 1 and 2 are congruent. They would be corresponding if we had those lines cut by that transversal, so we know that those two lines would be parallel. All right, forget that. What if 3 and 8 are congruent? 3 and 8, so we kind of see, maybe ignore a bit of it. 3 and 8, if we ignore this other line, those are alternate exterior angles to these two lines. So that would say that line L and is parallel to line M. And so that would be the converse of the alternate exterior. So I'm just going to write the converse of alt ext angles pos. So really shorthand, but this one up here, converse of the alternate exterior angles. So sorry, that's a theorem. Postulate is the corresponding. That we can prove this one from this postulate. So that actually is a theorem. So I'm going to write THM to abbreviate that one, theorem. All right, what about 3 and 5? 3 and 5 are vertical angles. So can we prove any lines are parallel? No, we got nothing. That doesn't tell us anything about the relationship. All that really says is we got two lines that cross. That doesn't tell us anything is parallel or perpendicular or anything like that. But what about measures of angle 1 and 5? If we know that those add up to 180, if we know that's true, then those are same side interior or consecutive interior angles to these two parallel lines. So that would be lines L and M again. So line L as parallel to line M, and that would be number 4 down here, the converse of the consecutive interior angles theorem. All right, and so then a couple other setup ones. We got refining angle measures using properties of parallel lines. So in this one, they are actually telling us that R and S are parallel. So or basically they aren't telling us that they're parallel. They're asking us to find what X and Y would have to be. So in this case, X. What would X have to be to make those lines parallel? Well, to make those lines parallel, we know that these two things, since those are same side and they're on the interior of R and S, that those should be supplementary. They should add up to 180. So if we set that up, 98 plus 3x minus 17 should equal 180. And so we could do this a couple of ways. We could subtract 98 first and then deal with this, or we could actually combine like terms. These parentheses have no effect. They aren't affecting order of operations at all, so we can just kind of ignore that and combine these like terms. 98 minus 17, so I'm going to have 3x. I'm going to write, we tend to like to write the x's first. The 3x, and then 98 minus 17 puts us at 81. So this is going to be positive 81 is equal to 180. And then we subtract the 81 from both sides. 3x is 99. And then divided by 3, x is 33. So x should be 33 in order to make those two lines parallel. This one is way more difficult. All right, so we want to make these lines parallel. Well, I could kind of try and set something up right away here. I know that like these two here, if I think about just this line here, if these are parallel, then this and this should be supplementary. So we could set up some sort of equation like 3x plus 2y plus 80 should equal 180. And so then another way we could continue with that is we could say 3x plus 2y should equal 100. But I can't solve for x or y. All right, so we're going to need to go beyond just that because we got two variables. If I had one variable, one equation, we can solve. If I got two variables with one equation, I can't. In one equation, we can't solve that. All right, so then we can set up another relationship here on this other line. With this transversal across those two lines, these would be corresponding angles. So I know that those should actually be equal. So the other relationship we can set up is 4x minus 2y should be equal to, these should be congruent if these lines are parallel, should be equal to 40. So if they're parallel, this statement should be true. And again, that equation in isolation, I cannot solve. I can't, there's two variables here, I can't isolate a variable. But what we've got here, if we have two variables and two equations, is going back to some algebra now, we can solve. This is a system of equations. So we have to solve kind of both of these simultaneously to make x and y be the right things to make these statements true. So there's a few things you can do: elimination, substitution, graphing. There's several different ways of solving this. This one sets up particularly well for elimination. So remember, this is where, because I have positive 2y in here and negative 2y here, we effectively add the left side of this equation to the left side of this equation, and my y's will cancel. And I get to add the right sides as well. So if we add 3x plus 4x, we get 7x. Negative or positive 2y plus negative 2y cancels, and we end up with 140. Now I'm down to, because we've eliminated a variable. You could also do, like I said, substitution. You could solve for x or y and plug it into the other, and that would eliminate a variable. But this is by far the easiest way of doing this one, I think. We've eliminated a variable. We're down to just x. We can divide by 7. So 140 divided by 7, and we get x is 20. We're not done yet, though. We know x is 20. We need to go back and figure out y. We could do that by plugging into either equation. I'll tend to choose the one that's got the smaller numbers and the positives, so I'll choose this one 3 times, and then this is where I'll plug in 20, right? So that 20 got plugged in for the x. So I'm using this thing here, plus 2y. So I still need to figure out what y is, equals 100. So we plug that in, so we get 60. Plus 2y is 100, and so subtract the 60, 2y is 40, divided by 2, y is 20. So in that case, we actually get x needs to be 20 and y needs to be 20 in order to make those two lines parallel.